In this video, I'm going to walk you through how to draw the shape of any molecule using a simple step-by-step process, as well as utilizing a template. Before we look at the examples I have in mind for today, let's take a look at the rules that I'll be following. So there's three simple rules. Number one, the first thing you have to do when faced with a question that says, determine the shape of XYZ molecule, is to do a dot and cross diagram. Then once you've got the dot and cross diagram, the next thing to do is determine the number of lone pairs, LP, and the number of bonded pairs. Then, once you know the number of lone pairs and bonded pairs, you can refer to the template and derive the shape. Now, the template I have attached in the description below this video, but basically what it works on the basis of is once you have the total number of electron pairs, you then divide it into those that are bonded and those that are spare pairs or lone pairs, and then that determines the overall shape of the molecule. Now, with shapes of molecules, you have a central atom, and then you have atoms bonded to that central atom, and the bonded pairs usually determine the shape of the molecule. However, with the presence of lone pairs, that can influence the shape, and especially the bond angle. It's important that you consider both types of electron pair. And just to remember also that when you replace a bonded pair with a lone pair, you subtract 2.5 degrees from the bond angle. Now, before we look at the example, there's one other thing to say. So also remember this. If you have an example which involves an atom in period 3 or down in the periodic table, these atoms can undergo what is called expansion of the octet. So what does that mean? Expansion of the octet means they can have more than 8 electrons in the outer shell. So for example, chlorine and bromine and some of the transition metals, they can have more than 8 electrons in the outer shell. And the reason why is because these atoms have access to the d subshell. And in the d subshell, there are 5 d orbitals with a total capacity for 10 electrons. So if, for example, you take sulfur or phosphorus, you've got the d subshell where potentially you could have 10 electrons. Then you've got the p subshell where you can have 6 electrons, and then the s, which can have 2. So then that gives rise to a total of 18 electrons, which is 9 pairs. So you'll find sulfur bonding and having 10 electrons in the outer shell or 12, and it's all because of this access to the d subshell. And then further down the periodic table again, you can have the f subshell, which pushes that number up even further. So with that said, let's get into the examples. So let's start with xenon tetrafluoride. First of all, dot and cross diagram. Don't worry, this is not meant to look pretty, you just get the atoms down. So we know fluorine is in period 2. So that means it can't have more than 8 electrons in the outer shell, and fluorine only needs 1 to complete the outer shell anyway. So we put the fluorine electrons in, which are shared, like that, and then fluorine is left with a full outer shell of 8. So that's the fluorine sorted, and we can see in doing this, xenon has used 4 of its electrons. Well, xenon is in group 8, so if it's used 4 of its electrons, that means it's going to have 4 electrons left over. As you can see in my diagram, there are 4 bonded pairs, there are 2 lone pairs, so that's a total of 6 pairs. And then if I refer to my template, I can see that when you have 2 lone pairs and 4 bonded pairs, the lone pairs arrange themselves 180 degrees apart to minimize repulsion, which leads to a square planar shape. So xenon tetrafluoride looks like this. You have like a fluorine there, another one there, and another one there. So basically, if I do a little square like that, kind of looks like that, right? Let me just get rid of that for clarity. And then you have the lone pair electron at the top and another one at the bottom. So as a shape, imagine this is like a piece of paper and the xenon is in the middle. And then you have this lone pair sticking out the top and then a lone pair sticking out the bottom. Bond angle would be 90 degrees angle there because it's based on a square. Okay, so that's the first example. B, Cl3+. So same thing again, just get the dot and cross diagram down, and I know that chlorine is in group 7, so it needs to gain just 1 electron to complete the outer shell. So let's do the outer ones first. So that's dot and cross, and then same for this one, the dot and cross. So that's those 2 N chlorines sorted. Now I can see that's positive, so that tells me an electron is missing. So one of the chlorines is missing an electron. So the central chlorine, it's used 2 electrons. So ordinarily it would have 5 left, but the 5th electron, which is that one there, that is not going to be there because there's a plus charge indicating that it's missing. That means that electron is not present, and that is what is needed. So now chlorine has 8 electrons in the outer shell, and then we denote the fact that it's charged by having a plus on the outside. So I can see there are 2 bonded pairs, there are 2 lone pairs. So that's 4 pairs altogether. And if I look at the template, this one is basically the same shape as water, which is V-shape or bent. So it kind of looks like this, Cl, 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 dot, 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 with a plus on the outside, and a bond angle of around about 104.5. Right, finally, let's try another atom that can expand the octet, which is sulfur. Sulfur and oxygen share the same thing in common, which is they are both in group 6. So they need 2 electrons to complete the outer shell. If you think how that can be achieved, which is something you might have done at GCSE, it can either have 2 single bonds to get the 2 electrons or 1 double bond. So sometimes when single bonds don't work, you might have to try a double bond, or you might have to try, a triple bond if it's something else, just to get the completed outer shell with no unpaired electrons, so that it's not a radical. So let's begin with sulfur, central atom, oxygen, oxygen, and I can see if I try a single electron with oxygen, let's use crosses for oxygen. Oxygen has 6, so 1, 2, 3, 4, 5, 6. You can see the problem I have. It's left with an unpaired electron, and it's a radical, and it doesn't have a full outer shell, so that is not going to work, which means that oxygen is going to get its full outer shell by a double bond rather than a single bond. And then the same for the other one. And then sulfur. Sulfur's got 6 electrons. Well, we can see that it's used 4 already, 2 with 1 oxygen and 2 with the other, which means it's going to have a pair left over. So my final diagram shows me there is 2 bonded pairs and 1 lone pair. By the way, a double bond counts as a single bond, so you don't count it twice. It's just treated as a bonded pair. So there's 3 pairs. So ordinarily, that would be a trigonal planar shape if there were 3 bonded pairs. But one of them is non-bonded, it's a lone pair. So we're going to have the V shape again. And it's going to look something like this, with the lone pair sticking out the top. And then the bond angle will be, if it was trigonal planar, it would be 120. But because a lone pair has replaced a bonded pair, to work out this bond angle, it will be 120 minus 2.5, which is the angle you take off when a lone pair replaces a bonded pair, equals 117.5, so approximately 118 degrees. V-shape, similar to the one above, but look, they have different bond angles. One is 104.5 and the other is 118. So I hope this video has been helpful today. If you have any questions or you're stuck, please comment down below and I will help you out. Check out all of the other content I produced on chemistry, science and other bits. I'm sure you're going to find it helpful and I look forward to seeing you in the next one.